Hi everyone. In this lecture, I would like to show you how machine learning and AI techniques can be used to discover new algorithms or new mathematical results. As was mentioned, I work in the science team of DeepMind, and here I will be presenting work that has been done by many people within DeepMind. This lecture will have roughly two parts. In the first part, I will present a concrete case study of how we can use AI and reinforcement learning techniques to discover new algorithms specifically for multiplying matrices. And then in the second part of the lecture, I'll talk more about the method underlying this work, reinforcement learning and AlphaZero, and Monte Carlo tree search. So before starting on the technical content, I would like to briefly mention the context of this work. Why has DeepMind even worked on this? So the mission of the company is to solve intelligence in order to advance science and benefit humanity. And the science team that I'm myself part of is really concerned with the second part of the mission here, so advancing sciences. What we try to do is we take the advances in AI and try to apply them in different sciences in order to bring benefits to humanity. And more concretely, we have different sub-teams within the science team that try to do this for different branches of science. So for example, maybe the most well-known example is in biology, where a system called AlphaFold has solved the problem of protein folding, and we are trying to do similar things in other branches of science, including chemistry and physics. Whether in mathematics, we have work that shows how machine learning can be used to aid the intuition of mathematicians. And then myself, I work in the team that tries to do this within computer science itself. So use AI techniques to discover new results in theoretical and practical computer science, in particular to discover new algorithms. So more concretely, the specific goal of my own team is to discover new, provably correct and efficient algorithms for impactful problems using machine learning. And there are a few key keywords in this mission. One, we really want provably correct algorithms. So we want to discover something that's a piece of source code that we are sure works for every instance. We are not interested in this case in approximations, neural or otherwise. We want, of course, these algorithms to be efficient and solving important problems. Now, in general, within the science team, when we decide what sort of problems to work on, we try to identify problems that we call root node problems. What this means is that these are problems that sit at the root of the tree of knowledge, in the sense that if you manage to make some advance on this particular problem, it will immediately have downstream implications on many other problems. And the particular case of matrix multiplication as a computational operation is such a root node problem, because matrix multiplication is used as a computational primitive, as you know, in many other computational tasks, including things like solving linear systems in simulations, and importantly also the training of neural networks, which is of particular interest to a company like DeepMind. Beyond that, matrix multiplication is, of course, also underlies many practical applications. Many apps on your phones and desktop machines will also be performing large numbers of matrix multiplies under the hood, of course. Now, matrix multiplication is such a well-known and basic operation. You might be asking yourself, what is there even left to discover? So to answer that question, let's have a look at what matrix multiplication algorithms actually look like. So on the left, I'm showing the operation of multiplying two matrices A and B together to form the output matrix C. I'm showing the case of 2x2 matrices here. And the algorithm that we have learned in high school for computing this matrix product, I'm showing on the middle of the slide. And this algorithm, it consists or contains 8 multiplications between entries of the two input matrices A and B, age 1 up to age 8. The reason being that to compute any of the 4 entries of the output matrix C, you have to compute the scalar product of two length 2 vectors. And for example, as you know, the upper left entry of the output will be the inner product between the first row of A and the first column of B. And within that inner product, you have 2 multiplications. So in total, there will be 8 multiplies to carry out. And for a long time, people have thought that this is actually the optimal or maybe the only way to multiply matrices. And so it was quite a big surprise when in 1969, the German mathematician Volker Strassen presented an algorithm that I'm showing on the right, which only uses 7 multiplications between elements of the input matrices A and B. Now, intuitively, this algorithm on the right, it might look more complicated, but actually it turns out that for matrix multiplication, the number of multiplies inside the algorithm is a much more important quantity for its overall efficiency than the number of additions or subtractions, as we'll see later. So it's really important that this algorithm only contains 7 multiplications instead of 8. And intuitively, you can think of this Strassen's algorithm as kind of a clever way of preparing these 7 ingredients, these 7 multiplies, where each ingredient is the product of some linear combination of matrices from A and some linear combination of entries from the matrix B, and then multiplying them together. And these 7 ingredients are chosen in such a clever way that then you can take different combinations of these ingredients, and just by adding or subtracting them from each other, you build up the correct result, so the 4 correct values in the output matrix C. And indeed, to verify that Strassen's algorithm is correct, all you need to do is to actually add up these terms, multiply out the brackets, and you will notice there will be some convenient cancellations, and you get the correct answer. Now, for 2-by-2 matrix multiplication, mathematicians have been able to prove that actually Strassen's algorithm is finally optimal. So it's not possible to do this with 6 multiplications instead of 7. But already for 3-by-3 matrix multiplication, the space of possible algorithms is just so immense that we, to this day, have no idea what is the smallest number of multiplications to multiply 2 3-by-3 matrices. We only know that this number is somewhere between 19 and 23, but there is quite a big gap. Now, importantly, here I'm talking about very small matrices, 2-by-2 and 3-by-3. But these algorithms, they can actually be applied to multiplying matrices of any size through recursion. So let's say we have a matrices of size n by n, 2 of them, A and B. Then we can think of these 2 matrices as block matrices. So we can partition these matrices into 4 blocks each, so that these matrices actually look like 2-by-2 matrices. But each entry within the matrix is actually a matrix itself of size n½ by n². And then we can apply Strassen's algorithm on this level, on the level of blocks, recursively, which means that we'll have to do 7 instead of 8 recursive calls. And that's why we get this huge saving in the time complexity of the algorithm, because by saving 1 multiplication in the algorithm, we are saving 1 recursive call. And then we can theoretically analyze the actual asymptotic time complexity of the resulting divide and conquer recursive algorithm, and show that Strassen's algorithm has a time complexity of big O of n to the power of log base 2 of 7, which is n to the power of 2.81, rather than n cubed, which would be the time complexity of the naive algorithm that we learned in school. Now, Strassen's discovery has, of course, spurred an entire research field trying to answer this question. So what is actually the fastest way to multiply large matrices asymptotically? And over time, people have come up with algorithms with smaller and smaller exponents. So we have Strassen's algorithm here with a time complexity of n to the power of 2.81. And over time, people have come up with faster and faster algorithms. In fact, the world record of 2.37 is work just from last year. However, there is a catch. These algorithms that achieve the best time complexities, they actually utilize very sophisticated mathematical constructions, theoretical constructions through group theory. And these algorithms are actually extremely far from being practical at all. They would only be faster to multiply matrices that would have size larger than the number of atoms in the universe, something completely crazy. So these algorithms, they've actually never even been implemented on a computer, as far as I know, because they would never actually make sense to be used. So there is an open question of, are there algorithms which are both practical and fast at the same time? And that's the question that has driven our work and the question that we try to answer. So how can one even start with answering this question of, does there exist an algorithm or doesn't there? And it turns out that for matrix multiplication specifically, there is a very elegant formulation of the problem of the space of possible algorithms for multiplying matrices. And it hinges on the following intuition. In general, when we have a linear operation, meaning there is a linear operation between two vector spaces, let's say between r squared and r squared, this linear operation can be represented by one fixed matrix. So for example, the operation of rotating by 45 degrees is represented by a fixed matrix. It's a 2D matrix. If we have a bilinear operation, bilinear means it's an operation that takes two inputs, and the operation is linear in both of those inputs separately. And matrix multiplication is precisely an example of a bilinear operation. Like to multiply two, you multiply two matrices, so there are two outputs, A and B, and the resulting matrix C, it's linear in both inputs. Then if we have a bilinear operation, that operation can be represented by a fixed three-dimensional tensor. So it's the same idea as for linear operations, but because we have this additional input, the representation has one additional dimension. So this is just for intuition, but I will explain precisely what this tensor, this fixed tensor that represents the operation of multiplying matrices looks like and what it contains. So let's have a look at that. Again, I'm showing the operation of multiplying two 2x2 matrices together. And this will be the tensor that represents this operation. This is a 4x4x4 tensor, because there are 4 elements in the first input matrix, there are 4 elements in the second input matrix, and there are 4 elements in the output matrix. So the axes of the tensor, they are indexed by the elements of the first matrix, second matrix, and output matrix. Now this is a binary tensor. It only contains zeros and ones. Zeros are shown in gray, the ones are shown in blue. And again, this is a fixed tensor. It's independent of the values inside the matrices that we actually want to multiply. And now, what do the zeros and the ones represent? So intuitively, the ones represent the locations where we need to take a product of two elements from one input matrix and the other input matrix, and where this product should be added to in the output. So concretely, let's have a look at the lower right entry of the product matrix C. It should be computed as the inner product between the second row of A and the second row of B. So in particular, there is a term where we multiply A21 and B12 together, and we will add that to this term. And indeed, we see that in this tensor, we have a 1 in the position that's indexed by A21, B12, and C22, indicating that this term appears in the matrix product. And similarly, for the other term in the dot product, we have the corresponding 1 entry in the tensor. Now, this tensor, it only represents the operation of multiplying matrices. It doesn't tell us how to carry out this operation, what algorithm to use. So if we have a specific algorithm, like Strassen's, I'm just showing it again on the slide, then it turns out that in this tensor language, a specific algorithm corresponds to what is called the low-rank decomposition of this tensor into a sum of rank 1 factors. Now, this concept of sum of rank 1 factors, it's the same as for matrices, but here, within each factor, we have the outer product of 3 vectors, because we have a 3-dimensional tensor rather than a 2-dimensional matrix. And more specifically, in this decomposition, there is one term for every ingredient in the algorithm, or every multiplication in the algorithm. And what the 3 vectors in the outer product represent is that the first vector encodes which elements from the first input matrix A to include in this product. The second vector indicates which elements of the second input matrix to include in this product. And then the third vector, it tells us to which entries in the output C we should add the product to. So here we have 1001, so we add it to see the first and the fourth entry of the output matrix. And similarly, we have this for every element in the algorithm. And the statement that Strassen's algorithm is correct, it just corresponds to saying that this decomposition is a valid decomposition of this tensor. So we have an equality here. And so in this tensor language, Strassen's discovery of 1969, we can rephrase it as saying that this matrix multiplication tensor of multiplying two 2x2 matrices has rank 7 instead of 8, meaning that it can be decomposed into 7 rank 1 terms rather than 8. So to summarize all this, we can phrase the problem of discovering algorithms for matrix multiplication as the following simple mathematical problem. We are given one fixed tensor T, which is this matrix multiplication tensor, and we want to find the decomposition of this tensor into a sum of rank 1 terms, and we want to have as few terms in this sum as possible. So we want to minimize capital R, because every term in the sum corresponds to one row in the algorithm, one multiplication, and we want to minimize the number of multiplications in the algorithm. So now comes maybe the main idea of this work, how we can use AI and machine learning techniques to discover new algorithms for matrix multiplication. And it is to turn this mathematical problem of decomposing tensors into sums of rank 1 terms into a single-player game. So in this game, the state of the game, or the board, you can think of it, will be three-dimensional. And at the beginning of the game, it will be set exactly to the matrix multiplication tensor. So the game board is a three-dimensional grid of numbers, initially the matrix multiplication tensor. And then in each turn of the game, the player will choose their move, which will amount to choosing these three vectors, u, v, and w, which describe through their outer product one rank 1 term in the decomposition, or in other words, describe one row in the algorithm, or one ingredient, one multiplication in the algorithm. And now what's nice about this formulation is that after the player has chosen their move, it's actually very easy to compute the new state of the game board. Because all we have to do is we take the previous state of the game board and we subtract this outer product of the three vectors that the player has written down, and then we get the new state of the board. So in green, I showed the elements that changed. And this is then repeated. In each step, the player chooses their move, and we subtract the outer product. And the game will end when the player manages to zero out the whole tensor. So the full game board will be just all zeros. And when that happens, the player must have discovered a valid decomposition of the matrix multiplication tensor into a sum of rank 1 factors, because we started with the matrix multiplication tensor, and in each step we subtracted one rank 1 factor and we arrived at the zero tensor. So the things we subtracted must form a valid decomposition. And there are as many terms in the decomposition as many steps it took the player to reach the zero tensor. So the goal of the player in this game is to reach the zero tensor in the smallest number of possible steps. And in machine learning terminology, we encourage the player to do this by giving the player a reward of -1 for every step that the player takes. Now, I showed you how this problem of discovering algorithms for matrix multiplication can be mathematically rephrased as finding low-rank decompositions of a particular tensor, and then how this decomposition problem can be phrased as a single-player game. And I illustrated all of this on the case of 2x2 matrix multiplication. And I already mentioned for 2x2, we already know the optimum. The smallest number of multiplications is 7. But actually, everything works in the same way if you try to solve larger cases of matrix multiplication, like 3x3. The only difference is that the tensor that you need to decompose is larger. So in this artistic visualization, I'm showing a tensor of size 16 by 16 by 16, which corresponds to multiplying 4x4 matrices. And you can maybe intuitively see that this is not an easy game. It's quite challenging, at least for me, to even understand what's going on in this tensor, not even to find a low-rank decomposition of it. But the good news is that, as I will show, it's possible to train reinforcement learning agents that are able to understand even tensors that are this complicated, and as a result, discover algorithms that are quite long and complex. They're not even readable on the slide. Now, it's not a coincidence that I framed this problem as a single-player game, because DeepMind as a company has a lot of history and experience with developing reinforcement learning agents for playing games. The probably most famous example is the first system of AlphaGo, which was a reinforcement learning agent that managed to defeat at the time the best human player in the game of Go. And following that, the company has developed like a next version of the system called AlphaZero, which generalized to multiple other human games, such as chess, shogi, and Go itself. And it managed to play all these games without any prior human knowledge encoded, such as expert games. That's what the zero in the name refers to. So it would be a very natural question, can we just take a system such as AlphaZero and apply it to this single-player game of finding decompositions of a specific tensor? And that, of course, we have tried, but it turns out that this is a much more challenging game. And the reason is as follows. So here I show the comparison of different variants of this game for discovering algorithms for multiplying 2x2 matrices, 3x3, 4x4, 5x5, and the comparison to the game of Go itself. Now, in terms of the episode length, so how many steps there are inside one game, the tensor decomposition game is actually not more difficult, like the games are even shorter, but it's much, much more harder in two other aspects. One is the size of the game board. So in the game of Go, it's a two-dimensional board of size 19 by 19, but in our case, it's a three-dimensional board, as I mentioned previously. So even just understanding what's going on in the current state of the game is orders of magnitude more challenging. But actually, the biggest challenge of these tensor decomposition games is in the size of the action space. Whereas in the game of Go, at every single step, there are at most 362 possible moves where you place your stone on the board, or maybe you can give up. In the tensor decomposition game, at every single step, remember the player needs to write down these three vectors, u, v, and w. And within each vector, you can arbitrarily choose every element of that vector. So the number of possibilities, even if you restrict to some finite set of possible entries, is just immense in every step of the game. So even though Go was already very challenging, this puts the difficulty on a completely new level. In addition to that, there are some specificities and challenges related to the fact that this is a mathematical problem rather than maybe a human game. For example, there is no training data that we could initially use to bootstrap our system. Like at least in the initial version of AlphaGo, there was a database of human expert games that we could use to pre-train the first version of the model. For decomposing tensors, there is no such data set, or certainly not a large one. Another thing is that we are only interested in decomposing one tensor. We have this one matrix multiplication tensor that we want to decompose. And if we just have an agent that tries to decompose this tensor over and over, then unless we explicitly make it explore through randomness, it will just keep playing all the same games all over. There is no second player to introduce some variability in the game so that the agent can explore new strategies. And also, there are many symmetries in this problem, as I will talk about in more detail later. And this can be both a challenge or an opportunity, depending on where the symmetry arises inside the problem. So the way we tackled this more difficult game was to build a system called AlphaTensor, which is an extension of AlphaZero, which has some key new components that I will talk about later, which allow the system to tackle these much more challenging games. And I will talk about these ingredients later on, but for now, just like the high-level overview of the system. In AlphaZero, we have a two-component system comprising acting and learning. In acting, we'll have a bunch of machines playing this tensor decomposition game from the beginning all over. And this is actually where most of the compute is spent when training a system such as AlphaTensor. These actors will be playing the games, and then when the games are finished, they will be sending these games to the learner, where these games will be used to update a neural network, improve the neural network. And then this improved neural network will be sent back to the actors, where the actors will use this improved neural network to hopefully play slightly better games than what they played in the previous iteration. And as a result, we'll sustain this self-improvement loop, where the actors always play slightly better games than before. Then we send those games to the learner improves the neural network, sends it back to the actors. So I will talk about that in more detail in the second part. But now, just to illustrate what kinds of results in computer science can one obtain when using a reinforcement learning system like AlphaTensor. So we applied AlphaTensor to discovering matrix multiplication algorithms for different base matrix sizes. And so multiplying an m by n matrix with an n by p matrix, so including these rectangular cases where the matrices are not square. And I call these base matrix sizes because, as I mentioned previously, all these algorithms, they can also be applied to much larger matrices through this recursive construction, divide and conquer construction. And in this table, I'm showing the previously known smallest number of multiplications required to multiply matrices of that size. So here we have Strassen's algorithm for 2 by 2 by 2 by 2 using 7 multiplications. And then larger numbers for the larger cases. And we trained an AlphaTensor system from scratch. So we didn't tell AlphaTensor anything about these existing algorithms, not even about Strassen's algorithm. And as the system was improving, it was able to rediscover algorithms using the same number of multiplications than what humans have been able to come up with through the history of this research. And what's exciting is that as the system kept improving, over time, it also discovered algorithms that for some sizes of the matrices used strictly fewer multiplications than what had been known before. Now, just like in Strassen's algorithm, all the algorithms that AlphaTensor discovers, they use integer coefficients in the algorithm. And this has a mathematical implication that these algorithms can be applied to multiplying matrices over any ring or over any field, including the most common case of multiplying real-valued matrices. But in some cases, you might know that your matrices lie in some specific ring. For example, maybe you want to multiply binary matrices in arithmetic modulo 2. And because this is a reinforcement learning agent that learns to play a game, it's very easy to modify the rules of the game and, for example, say it's okay if you discover a decomposition of the matrix multiplication tensor that only works in arithmetic modulo 2. And so it's very easy to modify AlphaTensor to discover more specialized algorithms for a specific field, such as F2, arithmetic modulo 2. And in this more specialized case, it's been able to discover algorithms that are even faster, including for these like cubic cases where we multiply 4 by 4 matrices and 5 by 5 matrices. And in particular, this result of being able to multiply 4 by 4 matrices in arithmetic modulo 2 using 47 multiplications instead of 49 was particularly exciting because this was the first time that Strassen's algorithm has been improved on 4 by 4 matrix multiplication since the algorithm was invented more than 50 years ago. But when using reinforcement learning or machine learning techniques to discover new algorithms, yeah, question? So in this case, all the algorithms that we construct, they follow the exact same recipe that you'll just perform this many multiplications initially, and then you will add up these multiplications to different entries of the output matrix. So the algorithm will always have this same general flavor, and so all of these algorithms are easily implementable and they're practical, meaning that there's not going to be any crazy construction within the algorithm. It's always going to be of the same form. But it's still a good question, of course, because different algorithms which have the same number of same number of multiplications, they might still have slightly different properties because of how they use the hardware and so on. And those differences will be there, and we can actually exploit them. I'll talk about that later. But all these algorithms are easily implementable and practical. No. So for the general case, the matrices can be anything. It's only for the F2 case that they are binary. Yeah. Okay, so beyond discovering algorithms that are strictly better in some metric, it's also interesting that usually when using an RL agent, you discover a whole population of algorithms. And indeed, this is what happened in our case, that we didn't just discover one algorithm for every base matrix size that had some number of multiplications. We usually discovered thousands of non-equivalent algorithms that had the same number of multiplications. And this diversity of algorithms that you can discover, it has multiple implications. One is just theoretical. So in mathematical research, in particular within algebraic complexity theory, these matrix multiplication algorithms are fundamental objects that are heavily studied. So the fact that we understand a bit better this space of matrix multiplication algorithms is already of interest in itself. And one particular result I would highlight is that before this work, there was only one algorithm known for how to multiply two 4x4 matrices in the general case using 49 multiplications. And that one only way was to use Strassen's algorithm recursively twice. So that's why it's 49, because it's 7 times 7 is 49. But AlphaTensor actually discovered more than 14,000 provably non-equivalent algorithms, which are not related to Strassen's. So this is already of interest in itself within this field of mathematics. But then the second, slightly more practical implication is that when you look at discovering algorithms for small base cases, such as multiplying 2x2, 3x3, and so on matrices, and you discover a diverse set of algorithms for each such base case, then you can look at solving slightly larger base cases, let's say in this case up to matrices of size 12x12 and 12x12. And for each such base case, you can exhaustively search the different possible combinations of an algorithm for a smaller case and another smaller case, and which combination, when you put them together, gives you the best algorithm for the slightly larger case. And so indeed, that's what we have done here, and I'm showing for different, again, for different base matrix sizes M and P. On the vertical axis, the improvement in rank, so by how many multiplications we have reduced the best known bound. And horizontally, I'm showing the previously known rank, so the previously known best number of multiplications. And of course, the larger the number of multiplications previously, the more we have managed to reduce it by doing this procedure. And then third, and most practically, what's, I think, quite exciting about being able to discover a diverse set of algorithms is that we can deliberately encourage the agent to actually discover those algorithms that will be the most practical when you actually run them on some piece of hardware. And here it's actually very convenient that we are using a reinforcement learning formulation of the problem, because the agent is only driven through this reward. And the reward doesn't have to be differentiable. It can be anything. You can reward the agent for anything you want. And in particular, what we have done is that previously the reward of the agent was just the number of steps it took to find the zero tensor. But we can add an additional term to the reward, which we compute as follows. When the agent finishes playing the game, meaning it reached the zero tensor, we can take these vectors it has written down and actually construct automatically the algorithm for multiplying matrices that this game corresponds to. We can take this algorithm and immediately benchmark it on a specific piece of hardware, let's say a specific GPU. And depending on how fast this algorithm actually is, in practice, we give a reward. So if it's very fast, we give a larger reward. If it's slow, we give a smaller reward. And by doing this, we encourage the agent to narrow down its search from this diverse set of algorithms which have the same theoretical complexities, the same number of multiplications in the algorithm, towards those that actually make the best use of the, let's say, maybe the caching mechanism of the particular piece of hardware that you want to optimize for. And just as a flavor of the numbers, we can obtain algorithms that are between 10 to 20% faster when multiplying matrices of size bigger than roughly 10,000 by 10,000 on the hardwares that we tried, both the GPU and the TPU. Now, so far I talked specifically about just one bilinear operation multiplying two matrices. Yeah, question?
Maybe on other slides we'll answer this, but I wanted to ask, because like normally when you implement like matrix multiplication on GPU, use like vector registers for that, right? So in this case, when you showed us, like for example Strassen or etc., they didn't look like trivially vectorizable. Yeah.
Yeah.
So how do you do this? Where from do you obtain this speed up? Do you vectorize across multiple matrices, and this is like where the speed up came from, or?
No, that's a very good question. So what we actually do in these cases is that we do not apply the recursion all the way to the end. So let's say we are trying to multiply matrices of size 10,000 by 10,000. Then we do maybe one level of Strassen's algorithm, which will require us to multiply matrices of half that, so 5,000 by 5,000, 7 such recursive calls. But for those recursive calls, we will no longer use Strassen's algorithm. We will use the standard vectorized implementation on the GPU. So we only do 1 or 2 levels of Strassen in the recursion, and then we revert back to the naive algorithm. And the speed up that we obtain is for this procedure. Because yeah, it wouldn't make sense to apply it all the way down, because then you lose all the hardware optimization.
Okay, thanks.
Okay, so far I talked specifically about the one bilinear operation of matrix multiplication, but the framework, as I talked about, it actually applies to any bilinear operation. So any operation where you have two inputs and the output is linear in both. And just one slight generalization that showcases an interesting new phenomenon is the operation of multiplying a skew-symmetric matrix. So that's a matrix that if you transpose it, you get the negative. And you want to multiply that with a vector. For this case, there is no recursive construction. So unlike in matrix multiplication, it's not the case that if we discover a way to do this for 2 by 2 matrices, there is some recursive structure to make it automatically work for 4 by 4, 8 by 8, and so on. But what happens instead is that we can use AlphaTensor to discover algorithms or decompositions of the tensor representing this operation for some small cases. So it's n equals 3, n equals 4, n equals 5, n equals 6. And then we can visualize these decompositions using a well-chosen color scheme. Well, let's say we show the ones in blue, minus ones in red, and so on. And then it's very easy to spot for us as humans that there is actually a pattern emerging. And this pattern we can manually generalize to arbitrary n. And then we obtain an algorithm by human construction that actually works for arbitrarily sized inputs n. And I think this is an interesting example, because in many mathematical problems, mathematicians actually care about asymptotic results. They often don't care about the smallest cases. Or also in algorithmic cases, there is not always a recursive structure that you can make use of. But it can happen that you just solve the small cases, and then through discovering a pattern, you generalize yourself. Now, going beyond bilinear operations, reinforcement learning can also be used to discover algorithms for other types of problems more generally. I presented the work on AlphaTensor that's specific to bilinear operations, but just three weeks ago, a new work has come out of DeepMind called AlphaDev, which operates on the level of source code directly and is able to discover new algorithms for other fundamental operations in computer science, such as sorting lists, or hashing, and also other operations. And in this case, the game is not on a three-dimensional game board like in AlphaTensor. The game is directly in the space of source code. So each turn of the game directly writes down one line in the source code, and then the game finishes when the source code is correct. So this is just to flag that this line of approach using reinforcement learning can be generalized to other problems as well. Okay, now I will start the second part of the lecture, where I will talk a bit more about the underlying method that's under both AlphaTensor and AlphaDev. But if there are any questions in the meantime, I'm happy to take them now.
Yeah, I didn't quite get, because if you just make random actions, I guess it's very unlikely you find an algorithm that actually solves it. So how did you, maybe you said it and I didn't get it, but how did you initialize the model to first find the first solutions? Yeah, that's a very good question. It will be partially answered later, but just as a high-level answer is that if the problem is simple enough, let's say for 2x2 matrix multiplication, even random actions will actually sometimes hit the zero tensor, and so that's enough to get the first solution, and then you can improve upon that. When the problem is slightly more difficult, then the key ingredient that I will talk about later is that we generated some synthetic demonstrations. So it's actually possible to generate synthetic data which teach the neural network how to decompose tensors in general. And then we hope that these techniques will generalize and also apply on the matrix multiplication tensor. So there will be one ingredient that addresses specifically this point. Okay. Thank you.
Thank you. I was wondering if my understanding is correct. Given a specific data representation, there may be more or less efficient algorithm, even with the same number of operations, due to the RAM misses or other vectorization problems. I was wondering if would it be possible to use this approach to discover better representation given a fixed algorithm?
On some level, for sure. So the specific setup for AlphaTensor, which is looking for these low-rank decompositions of the matrix multiplication tensor, that would not translate directly to finding this representation of the data on the hardware. But in general, this is a search problem, and there is a well-defined reward, which maybe is, again, the benchmarking runtime. So for sure, a reinforcement learning agent could be set up to tackle this problem, but it would be a very different game, I imagine. So then we would need to see how challenging this game is in terms of the different characteristics, the size of the game board, the action space, the episode length, and whether there are some tricks we can play to initialize the agent so that it can learn to play this game well. But in principle, it sounds like it could be in scope, yeah.
So I want to ask, my impression for reinforcement learning is that when you have many steps, there are diminishing gradient problems. Do you ever encounter this, or are there, or you guys use some smart ways of circumventing this?
No, so I'll talk about the specific training procedure we use a bit later, but we do not suffer from the diminishing gradient problem. We train on each state separately, which has its well-defined training targets. I'll talk about that later, so it provides a good signal.
So I think my question was misunderstood. I was asking whether the tensor is binary in this case, always, because...
Right. So the tensor is always binary at the beginning of the game. The matrix multiplication tensor is always binary, but then after the player makes their first move, the tensor may no longer be binary after that first move. Yeah.
Okay, so you choose which cell to pick and with what ratio?
So inside the game, let's go back a bit. So at the beginning of the game, the tensor is always binary, but then the player will choose these three vectors, u, v, and w. Inside these vectors, you can have whatever you want. We use 0, 1, or -1. And then you form the outer product of these three vectors. So already this tensor might contain zeros, ones, and -1s. And then you subtract this tensor from this tensor. So after the first step in the game, you will have a tensor that has zeros, ones, -1s, maybe 2s. Yeah? But then in the subsequent step, the entries might increase. You might have a tensor that has 3s, -3s, and so on. The goal of the player is to zero everything out, but it might be that the most optimal way to do that is to first build up some large entries and then later kill them off. So, yeah.
Why not build smaller entries? Like, I mean, it could just be that the optimum is to choose like 0.33 somewhere or take a half and.
Yeah, it could be. Yeah. So in principle, the entries here could be anything. They could be rational numbers. They could be complex numbers. It's just like a choice we had to make to keep the problem tractable, that we picked a finite set of possibilities to use inside these vectors. But if we allowed for complex entries in these vectors, then also the tensor would have complex entries inside the game. Yeah.
Just one more question, just one quick question on the skew symmetric matrix and vector multiplication. Was it that the algorithms discovered were unique, that you were able to see them and make structure out of it, or were they chosen from a...
Yeah, that's a good question. They were not unique. We had to look a bit to find the pattern. Like, it was not like we just looked and it immediately looked like this. We had to search for it.
Thank you.
Hi, so I guess, so in practice, how, for example, practically usable this is for deep learning? Is there some sort of a caveat that it would make sense if my matrices are of size above 10,000, something like this, or?
Yeah, so there are some caveats which I think can be satisfied in deep learning scenarios. So for the matrices, they do need to be big enough, roughly on the order of 10,000 by 10,000. But this is a size that will appear in some deep learning workloads. It also depends on the precision that you need in your matrix multiplications, whether you use things like bfloat 16 or float 32. Different algorithms will be faster for different precisions. But if you are in the right setting, then yes, this is applicable and you can make it work. One caveat is that when we discover these algorithms that are between 10 and 20% faster for multiplying some matrices on some specific hardware, this is for the specific workload of just multiplying matrices in sequence and doing nothing else. In a deep learning workload, you will usually have some nonlinearities in between the matrix multiplies. And in that case, it might be a different algorithm for matrix multiplication that will actually be faster overall because of the nonlinearities that happen in between. So you might need to re-optimize your algorithm depending on what nonlinearities you have in between the matrix multiplies.
Thanks. Maybe a very quick abstract question. So is it known that all interesting algorithms can be expressed as this sort of tensor decomposition, or could there technically be some that you cannot reach with this abstraction?
So there are two answers to that. One is that for a small matrix size, a specific size, let's say 10 by 10, it might be possible that there is an even faster algorithm that cannot be expressed as a tensor decomposition. But it is proved that the asymptotically fastest algorithm can be achieved using a tensor decomposition algorithm. So at least when you care about large enough matrices, you can do it with tensor decomposition.
My question is a sort of follow-up to what we were saying right before. So if you could please go once more on the demonstration that actually playing the game assures you to find the best possible algorithm to solve the matrix multiplication. Yeah, I didn't really get the theoretical part out of it. How did you prove this thing?
Right. So we need to assume here that we went through this translation between discovering an algorithm for multiplying matrices into the problem of decomposing the matrix multiplication tensor into a sum of rank 1 factors. So here I'm just presenting this game that the goal of the game is given a tensor, find me a decomposition into a sum of rank 1 factors. And what this game is about is that in each step of the game, the player just writes down one of these rank 1 factors. The player writes down UVW. And so if the player manages to go from the matrix multiplication tensor by subtracting in each step this outer product to the 0 tensor, then the things that got subtracted in every step, they must sum up to the matrix multiplication tensor. Because you started with the matrix multiplication tensor, you kept subtracting something, you got to 0. So the things you were subtracting, they must decompose the starting point.
Thank you very much.
One quick question. I think you already answered it at least partially, but is it known if those two state-of-the-art algorithms from 2020 and 2022 do they admit the composition into those one-rank tensors? And if so, then why? I mean, I expect this composition to be made of a small number of components. So what makes those algorithms so complicated?
So this translation, I think, is theoretically possible, but it has never been done because it would be a low-rank decomposition of a huge tensor. So it would be a decomposition of a tensor representing, I'm making the number up, the operation of multiplying a matrix of size 10 to the 50 by 10 to the 50. So it would be a decomposition of a tensor that has size, 10 to the 100, and the decomposition would have a huge number of terms. So it would be a low-rank decomposition, but it actually would have very many terms, and it wouldn't be practical at all to implement it or run it.
So let me maybe ask another question. So I was wondering if you have some thoughts about searching for interpretable algorithms. So let me give you an example. So let's imagine that we don't know an efficient algorithm for sorting, like an log n algorithm, and we want to find one. Mm-hmm. So we could use something like this for I don't know, 10 sequences of length 10, and then see what it discovers, and maybe try to come up with some explanation or interpretation. But it's not clear if this would be really feasible in this case. So, and you also showed this nice visualization, I think in the next slide, with this these diagonal matrices, that actually this was the case, that you were able to interpret the results post hoc and generalize them. So I was wondering if you have some thoughts about basically automating this, if this is possible in some cases.
Yeah, two answers to that. None of them is a full solution. One is that to get this behavior happening, that the decompositions or the solutions for different values of small cases do have the same pattern, there is one thing you can do to encourage this, which is another ingredient I'll talk about later, that you train a single neural network that you then use for all these problem sizes simultaneously. And that will encourage the agent to discover the same strategies for the different sizes, and it makes it more likely that the solutions will have a common pattern that you can then manually spot and generalize. And you have to hope that this happens, no guarantees. The second approach you could try to take is something more similar to AlphaDev, where you discover the solution directly in code space. Maybe in that case, there is more hope that you can inspect the code, even if it's in a low-level language like assembly, and see how you might be able to generalize it to larger inputs. Again, no guarantees, but maybe makes it more likely that you'll be able to do that.
So I have one question. If you start doing this training and it optimizes, is there a risk that it goes to a optimal minimum from which it would have to take such a big step to get to another optimum? It just stays there and really doesn't change that much anymore. So is this a case where you kind of have to start with a billion random initializations and then one gets really good and a lot of others stay in optimum? And if yes,
it's a very good question, and it can happen on some levels, but it's not nearly as bad as having to launch a billion attempts. So first of all, maybe because of how the landscape of algorithms looks like, whenever you start a new experiment from scratch, it will discover good algorithms. Maybe not the best ones in all cases, but it will always find reasonable ones. So that's one answer. The other answer, though, is that indeed we were able to identify that there are local minima, and sometimes local minima with the same number of multiplications, but the algorithms in those two minima, they have very different mathematical properties. So this can also happen, that you launch one experiment and through like the random initialization, it will discover some kind of algorithms, and then when you launch it again, then it will discover a different kind of algorithms, and they'll be completely non-overlapping. So this phenomenon exists, but luckily the density of good algorithms is good enough that whichever direction you start walking, you will discover good algorithms, but you might discover a different set. And of course, it might also be that there is a very rare direction that we have never taken, which contains even better algorithms than what we have found so far. That is definitely a possibility.
Thank you.
Okay, so I think we can just continue.
Okay, thank you. So in the second part, I'll talk a bit more about the method itself and talk about these ingredients that make AlphaZero into AlphaTensor, which I think are quite general and applicable to solving other mathematical and search problems using RL, not just matrix multiplication. And hopefully it will be useful that we went through this concrete use case of discovering algorithms for matrix multiplication, because I will keep referring back to that one specific example just to keep things concrete. So just as a summary, I showed that the matrix multiplication algorithm discovery can be phrased as tensor decomposition, and that can be phrased as a single-player game. And then I'll talk about this AlphaTensor system that is able to discover complex algorithms like this one. And as I mentioned, AlphaTensor builds upon AlphaZero, which is one base algorithm that originally was able to play 3 different games, chess, shogi, and Go, without any human demonstrations. And in all cases, it's an algorithm that would start with being quite bad at playing that game, but then over time it would match the best human performance and eventually surpass it in different games. And maybe the most well-known component of AlphaZero or of AlphaGo is Monte Carlo tree search, which is what this animation is showing, where the agent starts with the initial state of the board, and then it imagines different futures, how the game might go, explores different possible moves, and then it decides on the move to play, and then this is repeated in every step of the game. So I'll talk in more detail about where this magic tree search happens and how it's used. But first of all, the overall big picture that I mentioned very briefly previously is that AlphaZero, it contains 2 main parts. The first most important part, where most of the compute is actually spent, is in the actors, which is a large number of machines, maybe tens or hundreds, and all these machines are doing is they just keep playing the game that we are currently trying to solve, in our case this tensor decomposition game. What each actor does, it starts with the initial state of the game, so in our case with the matrix multiplication tensor, and then it needs to decide what is going to be its first move. So the first move will be deciding on these 3 vectors u, v, w. And just to decide on this one first move, the agent will build this tree search. So it will examine possible moves it might possibly play, multiple steps into the future, and it will build this tree in a way that's guided by a neural network. So the neural network will suggest to the agent what kinds of moves it should consider. And when the tree is expanded into some node, into some future state of the game, the neural network will also be able to tell the agent how promising this particular state looks like, so that the agent doesn't actually have to build the entire search tree until the end of the game, which would be prohibitively expensive. So the agent will build this big tree, and then based on this big tree, it will just make a single decision, which is what's the first move that it should commit in the game. So in the game of Go, this would mean actually placing a stone on the game board. In our case, this means committing to these 3 vectors u, v, w, which correspond to the first move. When that happens, the state of the game is updated. So we will get a new tensor, a new state of the game. And the actor will have to do the same thing all over again. So from this new state, it will build a new tree search of possible futures just to decide on the next action to play in the game. And the actor will keep doing this state by state until the game finishes. The game finishes when it reaches the 0 tensor, or we have some artificial cutoff in case the actor is not able to find it. We just kill the game at some specific number of steps. And when this game is finished, so meaning we have a sequence of moves from the start tensor to the 0 tensor, or maybe an unsuccessful game, this game is sent to the learner, or it's stored in a buffer from which the learner can retrieve it. And the learner will then use this game to improve the neural network that the actor was using previously. So let me talk a bit about this role of the neural network in an AlphaZero system. The input of the neural network is the current state of the game. So in our case, it's this 3-dimensional grid of numbers, the current state of the 3D tensor. And the neural network has to encode this state of the game, and then it needs to predict two different quantities. One is the policy. So the neural network needs to predict a distribution over actions that it thinks the player should play given the current state. So for each possible action, it gives a probability of how likely this action should be played in the current state. And it should also predict a value, which is technically an estimate of what is going to be the future sum of rewards if the game continues to be played from the current state. Now, in the concrete example of tensor decomposition game, remember that the reward was just -1 for every step taken. So the future sum of rewards is the future number of steps until the game finishes with the 0 tensor. So this prediction, the value prediction, is what is the remaining number of steps to reach the 0 tensor from the current state of the game. So this is what the neural network needs to be predicting. And as I will describe later, the games that we receive from the actors are used to train this neural network and to improve it, to be better at predicting the policy, the actions to play, and the value, how good the current state is. Now, once the neural network is updated, it is sent back to the actors, as I mentioned previously, with the intention that this slightly better neural network will allow the actors to play slightly better games. As a result, the learner will receive better games than before, and the network will get even better. And this self-improvement loop will be sustained, and the agent will keep improving. So as I mentioned, the tree search actually happens on the actors and actors only, and there is one tree search carried out before deciding on every move inside the game. So let me now talk in more detail about this Monte Carlo tree search, which is a key component of the algorithm. So I will go through this slowly. So let's imagine we are in a situation that the agent has already played 3 moves inside a game. So this was the initial state of the game, the matrix multiplication tensor, and 3 moves have already been played. So the black circles correspond to states that we have already visited in the past, and currently we are in this purple state. And the agent is trying to decide what should be its next move from this state. And here I'm already showing a partially expanded tree search, but initially this would be empty. Initially there would be no children, but let's say we already have some. And so from this state, the agent has already constructed some possible futures of how the game might unfold, depending on different moves it might play. And I am showing nodes that do not have any children. They're called leaf nodes. And in general, this doesn't mean that the game is finished in these cases. It just means that we haven't explored what might happen from this state of the game onwards. But it might also happen that in some branch we have already went deep enough that we have encountered a state that's an actual terminal state in the game. So I'm showing that in red. So this might be a state that already corresponds to the zero tensor, meaning that there would be this path that leads to the zero tensor. But maybe somewhere else there is a shorter path. Okay, and now to actually run this algorithm, we'll need to maintain 3 different quantities in every non-leaf node in this tree. And these 3 quantities are as follows. So for every node, we'll store the prior policy. So remember, this is the prior policy is the prediction that the neural network gave us, the policy head of the neural network gave us when we queried it on that state. So whenever we query the neural network on this state, we remember the distribution over actions it gave us, and we just store it once and for all. We don't query the network again on the same state. Then for each state, we will also store the Q value, which will be the average value, the average prediction of the value from all the descendants of that node. So initially, it will be initialized to 0, but over time, we will keep updating it so that the value in every node is the average of the value predictions from all the descendants of that node. And here the idea is that the Q value, it should be a more accurate representation of how promising a given node is than compared to the policy prediction from its parent. Because the Q value is actually based on the values we have seen deeper down in the tree. So these values will be more accurate because they result from actually doing some exploration in the tree, going deeper down, and only querying the value network deeper in the tree when the end of the game is already closer. And finally, for every node, we'll also remember its visit count. So this will be the number of, you can think of it as the number of descendants of that node, or the number of times we have passed through that node when we descended the tree. Okay, so these will be the 3 quantities that we need to maintain. And the main crux of this MCTS algorithm is how to decide where to insert the next node to make the tree larger. But first a question.
How do you deal with duplicates, like nodes that recur more than once?
Yes, so it might happen that some nodes correspond to the same state. One thing is you could just ignore them, but we do have an optimization that just merges them together, in which case instead of a tree, you will have a directed acyclic graph. You can merge them. Yeah. Question.
You explore the symmetries of these Markov decision processes. It seems like most of the games that you are describing that have symmetries over state and actions. So your policy should be equivariant and your value function should be invariant.
There are some symmetries. I will talk about them specifically later. But inside MCTS itself, we do not explicitly exploit the symmetries.
Okay.
So it might be that there are 2 nodes which are actually symmetric, and we just keep them separate. Okay, so yeah, the main component of MCTS is deciding which branch of the tree to explore next, where to add a new node, and this is done using a concept called a simulation. So a simulation is the process of starting from the current state of the game, the committed node, the purple one, and somehow deciding how to descend this tree. So choosing in every step some child to descend down on until we reach a leaf node. And then this leaf node will be expanded by querying the neural network on this node, and we will get its children, and we will add these children into the tree. But how do we decide on where should this simulation go? Like which branch should it go down? And for that, we use a formula called the UCB formula, which is a formula that tries to capture this exploration-exploitation trade-off. So intuitively, we want to go down a branch of the tree that it's both promising, meaning that it's likely that we will find a higher reward path, meaning that we'll be able to reach the zero tensor in a small number of steps. But at the same time, we don't always want to go down the same branch of the tree. We also want to have some exploration of parts of the tree that haven't been explored much. And so this formula is a mostly a heuristic formula which tries to balance these two ambitions. So it's a deterministic rule. In every state, we'll choose to descend down the action that maximizes the following quantity. This quantity is a sum of two terms. The first term, you can think of it as the exploitation term, is just the Q value of that action. So this is how promising does that action actually look like, given the exploration we have already done so far. And then there is another term, which is the prior policy. So so this term captures how promising an action looked a priori, so how it was predicted by the policy network when we queried it in the state where we are deciding which action to go into. And then this term is weighted by the following fraction, including the visit counts, where the visit count of the action A that we are currently scoring is in the denominator. So if we have an action A that has already been taken many times, so let's say in that case, this action was already taken quite a lot of times, this fraction would be small because the denominator would be large. And so we would be deciding less based on the prior policy and more on the actual Q values. So it would be deciding more strongly based on how the different branches of the trees look like given the exploration compared to the initial prediction of the policy. And I should mention that this is maybe the main intuition of doing this tree search, that there is this policy which is called the prior policy, which is an estimate of how good an action is a priori. That's why it's called prior, because it's just predicting, given the current state, which action should I take. But then we try to improve upon this prediction by the policy head of the network by actually doing some look ahead, by building this tree search and accumulating the Q values, which will provide a better estimate of which actions are actually promising compared to this prior policy. Okay, so now we have this simulation rule. So this is a rule deciding where should the simulation go and where do we add new children in the tree. And so for every simulation, we expand the tree once, and we do multiple such simulations. In the largest variants of the game, we might do maybe 800 or even 1600 simulations to build this tree. And all of this, we build this tree just to decide on the one next action to actually play. So indeed, let's imagine that we have done whatever number of simulations we have decided to do. We have built this tree. And now we want to decide, remember we are still in this state and we are trying to decide which action to actually play in the environment. Where do we put the stone on the game board? Which 3 vectors do we write down? So we want to decide between these 4 actions. So we have built all of this tree just to decide on which of these 4 actions to take. And the rule that is most commonly used is one of these 2. We look at the visit counts of these 4 actions, so how big the subtree under each action is, and then we pick the action that either maximizes the visit count deterministically, or we pick proportionally to the visit counts with some temperature, if we want to have some additional exploration here. And here, again, the idea is that the visit counts are a more accurate representation of how good an action is than the initial prediction of the policy head in this state, which didn't have any look ahead available to it. But after we have done the tree search, the branch that got explored the most, it can be expected to be actually the best one or the most promising one to take. So in this case, the most visited child is this one. So we'll actually take this action in the environment and commit it. And so this state will become part of the history of the game. And in the next step, this becomes our current step of the game. And a priori, we might think that now that we are in this state, we need to start from scratch and build a new Monte Carlo tree search just to decide on the next action from this state. But what's nice about the particular cases that we are looking at here, which are deterministic games, is that we can reuse this part of the search tree from the previous tree search and keep it for the next iteration. So when we are trying to decide on what move to play from this state, we don't have to start from scratch. We can keep this subtree and just keep adding to that by, again, running many simulations, each simulation expanding another leaf node. Okay, so this is how we build the tree search, and we use it to decide which action to actually play in the environment. But there's another output of Monte Carlo tree search that is useful to us, and that's that it also provides us with training targets for the policy head. So when we will use the finished game to train the neural network's policy head, let's say when we want to train the neural network on what action to play from this state, we will not only train the neural network to predict the action that was actually played, which will just be a single action. We will train the policy head towards the visit count distribution. So we will try to make the policy head predict a distribution over actions, which captures the proportion of how many times these subtrees were expanded. So the idea here being that this is a more complete description of what makes a good action to play in this node, because it might be that from this state there are actually multiple good actions to play. So we don't just want to train the neural network to predict one of the actions that we actually chose, but we want the network to understand that there is a distribution of potentially good actions that it should model. Okay, now one aspect of MCTS that I found particularly confusing myself when I was first learning about it is that the concept of policy is quite overloaded. And in fact, there are 4 different policies that appear at different stages of the algorithm. So here I just wanted to summarize them and briefly go through them to highlight the differences and the terminology. So the first policy is the prior policy. So this is the policy that the neural network predicts on a given state. So you reach some state in the game, some state of the 3D game board, and you ask the neural network, what action should I play from this state? So that's a stochastic policy because it gives you a probability for every possible action. It's just a direct prediction of the neural network. But then inside MCTS, we had this concept of a simulation. So how should I descend the tree in order to decide where to expand this tree? That's a deterministic policy, and it's a policy that maximizes this UCB formula, so the trade-off between the Q values and the initial policy. There is no randomness in this. It tells you exactly how to descend the tree. Now, after you have done many of these simulations, you want to decide which move to actually commit in the game environment, and that can be either a stochastic or a deterministic policy. The stochastic one is you pick proportionally to the visit counts with some temperature, or you deterministically just take the action that was visited the most. So that's the committing policy or the acting policy. And then finally, there is the policy, which is the training label for the policy head. That's the policy that you want to mimic when you train the neural network. And that's just the policy where you are proportional to the visit counts. So these are the four different policies. Okay, so just to summarize where MCTS fits in the overall AlphaZero algorithm, MCTS happens in acting, so in the acting loop on top. You build one Monte Carlo tree search for every committed move in the environment. So before taking every move, there is a tree search to decide what move to take. And in deterministic environments, the subtrees can be reused. So the tree that you have built here, when you commit a move, you can keep part of that tree that lies under the move you actually took and use that to initialize the next tree search to save some computation. And doing this MCTS actually gives you 2 outputs. As I mentioned, the main idea is that it gives you a better distribution over the next action compared to the prior policy from the network. And this is used, one, to actually select which action to commit in the environment, as I keep mentioning, but also it gives you the training labels for the policy head. So those are the 2 outputs you get out of MCTS. In terms of the neural network, I mentioned that I will describe what are the training labels for the neural network. So just briefly, the neural network, when it receives games from the actors, is trained as follows. On a given state of the game, let's say this state of the game, the policy head will be trained using the standard softmax cross-entropy loss to mimic the visit count distribution from this state. So in this state, when we are deciding which action to take, we had this visit count distribution, so we'll train the policy head to mimic that visit count distribution. And for the value head, we will train the value head to predict the actual future sum of rewards from this state. So this game finished in some way, so from this state we can count or sum up the future rewards, and that will be the training target for the value head when we train the neural network on that particular game. Okay, so that just summarized here. And so as I was mentioning before, so far I described the AlphaZero system, but now we want to use it to tackle this much more challenging game of tensor decomposition. So we need some additional components that allow us to use this system for this much more challenging game. And in particular, I will describe 6 ingredients which basically turn AlphaZero into AlphaTensor. And all these 6 ingredients have this nice property that I believe they are quite general. So they're not specific to discovering matrix multiplication algorithms. They can be used when tackling different search problems or mathematical problems using reinforcement learning. So let me go through those 6 in turn now. The first key ingredient is developing a specialized architecture for your problem. So I must admit that personally I was initially maybe a bit skeptical about tweaking the neural network architecture. I thought we would be able to improve the results much, much more by thinking about the symmetries of the problem and being clever about the algorithmic parts. But I was repeatedly impressed by how good improvements in performance we obtained just by playing with the architecture, trying the different variants of the architecture and different ways of incorporating symmetries into the architecture itself. So it is really a key component of the entire system. And in the final version of the system, the architecture operated as follows. So remember the neural network, it needs to encode the current state of the game, which is a 3D tensor, and then predict a policy and the value. So we encode the 3D tensor as follows. We take the 3D tensor, and then we can project down this 3-dimensional cube along the 3 different axes into 3 matrices. Now these matrices will still be actually like 3-dimensional because they're matrices of embeddings, but intuitively they represent 3 different projections of the 3-dimensional tensor into 2D matrices. And then the main crux of the torso, the common part of the architecture, is a sequence of attention operations. But importantly, we do not perform full attention between all elements of the 3 matrices simultaneously, which would be very expensive. But instead, in each attention step, we only perform attention between elements in the matrices that lie in the same slice of the tensor. So for example, here in red, I'm highlighting the elements of the projections that all represent entries that lie in the slice of the tensor that's like furthest away from us. And this restricted attention pattern is both like computationally much cheaper than doing full self-attention on all elements at once, but also it performs empirically much better. And we can only speculate that the reason is that by doing this specific attention pattern, we have built in some knowledge about how tensors work and which elements of the tensor are more related to each other than others, that it leads to an empirically much better performance. And then after this sequence of attention operations, we extract a common embedding of this tensor, and then this final embedding is sent to 2 different parts of the network, the policy head, which is an autoregressive transformer, and the value head, which is trained with distributional reinforcement learning. It's a simple value head. So yeah, this was the importance of having a customized architecture. The second ingredient that I would like to talk about is the ability to generate synthetic demonstrations for many problems that have a decomposition flavor. And this is what I was hinting towards earlier when I was answering the question about kicking off the training at the beginning. So the observation is as follows. In many decomposition problems, including ours, the task is that we have some complex object, like maybe the matrix multiplication tensor, and we want to decompose it into a sum or a collection of simpler objects. So in this case, a sum of rank 1 terms. And this is, of course, a hard problem. It's the problem we're trying to solve. It's NP hard, in fact. But we can observe that going in the opposite direction would actually be very easy. So if I gave you some decomposition, computing the tensor that it corresponds to is trivial. You just need to do the outer products and add up the terms. It's super easy. So we can actually generate a large data set of synthetic demonstrations as follows. We sample decompositions completely at random. So we'll just pick a random number of terms, and for each term, we'll just sample these entries at random. So we'll get a random decomposition, and we compute its corresponding tensor. And we can do this as many times as we want, and it will generate us this. It will give us this unlimited stream of pairs, a tensor and a valid decomposition for that tensor. Now, of course, there is no guarantee that these decompositions are optimal. It might be that in some cases we have a suboptimal decomposition of the tensor, and also there is no guarantee that these random tensors will have anything to do with the matrix multiplication tensor. They might not be useful. But empirically, it turns out that this is a good enough procedure to kickstart the learning by training the neural network on these completely synthetic demonstrations, which have nothing to do with the matrix multiplication tensor, might even be suboptimal. And you can do the same thing in many decomposition problems, where going from a complex object to a simpler one is hard, but the other direction is easy. So the specific algorithm for generating an unlimited number of synthetic demonstrations, just quickly, is that for as many demonstrations as you want, capital N, you randomly pick the number of terms, and then within each term or within each factor, you just sample these entries U, V, W completely at random independently, and then crucially, you just add up the tensor by computing the outer products and summing them up, and that gives you a data point. The third ingredient I would like to talk about is the idea of diversifying the target. And the reason you might want to diversify the target is as follows. In mathematical problems, including ours, there is only one object we care about. So we only have this one tensor, the matrix multiplication tensor, that we want to decompose. We don't care about any other tensor. So you could say that maybe the test size in our machine learning problem is just one. There's only one test point. So what happens if we train our system and then it doesn't happen to work well on our single test point? And are we stuck? So what's nice about mathematical problems, they often have many symmetries. And you can take your matrix multiplication tensor and you can generate many other tensors that are equivalent to it by expressing this tensor in a different basis or a different coordinate system. So this is the same concept as for matrices. If you have a matrix representing a linear operation, you can express that linear operation in any other coordinate system, and that gives you a different matrix which is equivalent to the first one, meaning that it has the same rank, so it can be decomposed into the same number of factors, same for us. And if you find a decomposition of the matrix multiplication tensor in some other coordinate system, then it's very easy to transform this decomposition back into the canonical basis. So what this gives us is that we can generate these many other, let's say, views of the matrix multiplication tensor, or this tensor in other coordinate systems. And it suffices to solve any one of them, because if we find a decomposition in any one of that coordinate systems, we can easily turn it back into the canonical basis and extract our algorithm. And this has some very appealing properties from a machine learning perspective. In particular, it injects diversity into the games that the agent plays, because now, instead of always starting from the same matrix multiplication tensor in every single game, we always start from a tensor expressed in a different basis. So the games already will have some diversity baked in from the beginning. And also, it's quite appealing from the perspective of learning, that it might happen that maybe through luck, one of these views of the tensor will be much more similar or closer in distribution to the synthetic demonstrations from the previous ingredient, and it will be, for this reason or any other reason, easier for the neural network to solve. And it just suffices to solve that one, and we are done. So that's the idea of diversifying the target, increasing the size of the test set. The fourth ingredient is a high-level discussion of symmetries. I mentioned that symmetries can be either a challenge or opportunity, depending on where they arise in the problem. And in this particular problem, there are indeed many symmetries. The first one is the symmetry in the input itself. So the tensor, I mentioned already, it has the symmetry that you can express it in a different coordinate system. And this is an opportunity. You can use that to diversify the target and introduce diversity into the games that you play. We also partially used this symmetry in the input tensor to design the architecture of the neural network, but empirically we actually didn't find it useful to make the neural network architecture completely equivariant under this symmetry. That's just an empirical finding. Interestingly, there are also symmetries in the output side of the problem. So for example, on the level of a single action, remember in every step of the game, the player needs to output these three vectors, u, v, and w, and then the state of the game will be updated by subtracting the outer product, u times v times w, from the current tensor. And there is this annoying symmetry that if instead of u, v, w, the player predicts u minus v minus w, then it's actually the same action, because the two minus ones, they cancel when you do the product. And this is usually a very harmful symmetry in the problem when the agent can predict multiple actions which are actually exactly the same. They lead to the same next state. But it's very easy to solve, for example, through canonicalization. So you can impose in the rules of the game that when the player predicts these three vectors u, v, and w, then for example, the first non-zero entry of u and the first non-zero entry of v both have to be strictly positive. And then you break the symmetry and you lose this redundancy of possible actions. Another type of symmetry on the output side is on the level of a sequence of multiple actions. So for example, in the tensor decomposition game, we are looking for a decomposition of a tensor into a sum of rank 1 terms. And of course, addition is commutative. So it doesn't matter in what order you discover your factors. Like if you discover first the blue factor and then the yellow one, it's the same as the yellow one and then the blue one. So a priori, it might seem like this is also a serious type of symmetry that might confuse the agent. But empirically, we actually found that the agent very quickly finds its preferred ordering of the actions, and it always plays the actions in kind of the same order. So intuitively, you might think that maybe the agent first plays the actions that are more dense and then the sparse ones towards the end. So it finds some ordering that it latches onto and keeps playing with that ordering. So this symmetry didn't turn out to be harmful. And we were actually able to use this symmetry to benefit us in a small way, which is as follows. You can use it for data augmentation. So remember when the actor finishes playing a game, that game is taken and it's sent to the learner to improve the neural network. And what we can do is we can take this finished game, and instead of just sending it to the learner, we can make a copy of it. And in the copy of this game, we can apply this symmetry by randomly permuting some of the actions and sending this modified game to the learner as well. And this has the computational benefit that for the price of playing one game in the actors, we generate 2 games to send to the learner to learn from. The fifth ingredient that often arises in mathematical and search problems is that this is a slightly non-standard reinforcement learning setting, where we do not actually want to optimize the usual case of average reward or expected reward. What we care about is having one single game that achieves the highest reward possible. Or in other words, we care about having one game played by the agent that discovers an algorithm for multiplying matrices that's better than anything that has been known before. And we don't care if the agent also plays a large number of completely rubbish games, as long as there is one game that's really good. And this is different from the usual RL setting. It's also different from maybe the AlphaGo setting, where it would be quite embarrassing if the AlphaGo system went to play the world champion and then most of the games were really bad and there was just one game that's really good. So here we really care about the maximum reward rather than the average. And there are multiple ways we can exploit this. One is that we can deliberately make the agent more risk-seeking. And in particular, we did this when in the part where the agent predicts the value of a specific state. So when the agent reaches a state in the game, the neural network has to predict how promising this state looks like. What is the distribution of future rewards from this state? And because the value head is trained with distributional RL, we do not just get a point prediction of the, like a specific scalar number. We get a distribution of what the neural network thinks is going to be the future reward if we play from this game. And we form a risk-seeking prediction out of this distribution, where we only look at the top 25 quantiles of this distribution, so we're being very optimistic, and take the average of that. And the effect of this, of taking this prediction, is that the agent will be much more risk-seeking. So if there is a state that has some chance of being really good, we'll really encourage the agent to explore that state much, much more, even though on average it may not be as good. It's just that there is a chance that it's a really good state, so let's explore it more. Another feature of mathematical and search environments is that the environments are deterministic. And in particular, when you finish playing a game and the game achieved a really high reward, then you can be sure that this high reward is real. It's not a high reward that has been obtained because of some randomness in the environment or through some luck. It means that you really found a good solution. So it makes sense to train on this game much more often than on any random game that may not have as such high reward. And we implemented this just through having a separate storage or separate buffer of the best games so far. And we trained 5% of this time on this smaller collection of highest reward games. The final sixth ingredient that I would like to mention to you was particularly important to get the best results, and it was also very exciting to see it in action, and it is to train a generalist agent. And what I mean by this is that a priori you might think of training a separate agent for different sizes of the problem, let's say 2x2 matrix multiplication, 3x3, 4x4. But actually what happens to work much better is to train a single agent, a single neural network that is able to solve different sizes of the problem simultaneously, just through padding the smaller sizes to a larger size. And we are able to actually analyze the network that has been, or the agent that has been learned in this way, that was trained on multiple matrix sizes simultaneously. And we were able to confirm that the agent found some ways to transfer knowledge from one matrix size to another matrix size, even though there is no known mathematical relationship between those two matrix sizes that would facilitate the transfer. But the agent learned some tricks, which we cannot explicitly describe, about how to decompose tensors, that it was able to transfer to a different tensor and thereby improve the results. And finally, there's just one non-technical meta point, but which was a crucial ingredient nevertheless. And this ingredient is about being very clear about what your metric is and what you want to improve. And ideally having some sort of leaderboard that tracks your progress towards your goals. We set up a leaderboard like this for tracking the smallest number of multiplications we have discovered for different matrix sizes. And this was very motivational for the whole team to keep improving the results. But also importantly, in complex machine learning systems like this one, it's often the cumulative effect of small improvements that result in big advances. And so it's very important to have a mechanism in place where if you have a small improvement to your system, you can evaluate it that it is an improvement, even if it's a small one, and add it into the default configuration of the system so that future improvements build up on the previous one. Because it's only in the only if you add all these things together, you'll be able to see the big improvement in performance. Okay, so in summary, I talked about AlphaTensor, which is an extension of AlphaZero with these 6 key ingredients that go from AlphaZero to AlphaTensor. And just to give you an idea, out of these 6, there are 4 that are absolutely crucial. Without them, the performance degrades significantly. And this is having a bespoke architecture, the synthetic demonstrations, diversifying the target, so increasing the size of the test set, and training a generalist agent. The other two, they also gave improvements, but not as huge ones as the other 4. Okay, so in summary, I talked to you about how discovering algorithms for matrix multiplication can be phrased as this mathematical problem of taking a fixed tensor and decomposing it into a sum of rank 1 terms, and how this mathematical problem can be framed as a single-player game. Then I talked about AlphaTensor, which is an RL agent that learns to play this game, and it learns to play it well enough to be able to discover complex algorithms like this one. And to wrap up, I would just like to take a little bit of time to also talk about the limitations of this approach and related approaches. So one is that, as I mentioned previously, you have to make some assumptions for computational reasons. In our case, in the algorithms we discover, we had to choose some finite set of possible entries that we put into these vectors u, v, w, which correspond to the scalars you can use in the linear combinations when you take elements from the input matrices. And we just decided to use this set based on past experience with how these algorithms tend to look like. But this choice is, of course, limiting. It might mean that there are even better algorithms that use a different set of possible entries. And currently, we might be missing out on those. And more generally, because this is an RL system, there is no optimality guarantee at all. So even though we have discovered algorithms that either match or surpass the previously best-known algorithms, there is no guarantee that even faster algorithms don't exist out there. I would also like to highlight the generality of this approach on 3 different levels. On the level of problems that we can tackle. So the way I presented AlphaTensor, it immediately applies to any bilinear operation. But I believe many of the components I talked to you about, they actually generalize to other decomposition problems and other search problems in general. Those just would require a bit more work about setting up the game and tackling its specificities. On the level of different mathematical spaces that we can tackle, the method is very general, because changing the space just corresponds to changing the rules of the game slightly. So I already talked to you about being able to handle finite fields. So, for example, arithmetic modulo 2. You could also operate over complex numbers or any other space you can think of. And maybe most excitingly, this family of methods is very general on the level of objective functions, because the method is driven by this reward, which doesn't have to be differentiable. It can be anything you want. You can optimize for any property of the algorithm or any property of the object that you want to discover. It can be an arbitrary reward. Initially, we optimized for the number of multiplications in the algorithm, which corresponds to the theoretical time complexity. But I also showed an example of optimizing for actual runtime. You could try to optimize for other properties of the algorithm, like memory consumption or power usage, or maybe something else. And finally, the main takeaway, at least for us from this work, has been that it has inspired us and given us confidence that machine learning and AI techniques, like reinforcement learning and others, they can really go beyond human intuition and discover things that go beyond the current state of human knowledge and don't just necessarily imitate what's already in the training data. So I would like to invite you, if you like this line of thinking, to see whether maybe your problems can also benefit from any of these ideas. Thank you.
So now we have about 10 minutes for the Q&A session. So let me maybe start with a simple question. So basically about this last ingredient that you mentioned, the generalist agent. So I was wondering, have you used any curriculum for this one, or like basically the uniform mix of problems?
So we actually didn't have a curriculum that would change over time. But of course, it would happen that as we train on all these matrix sizes simultaneously, the agent first learns to tackle the small cases, and then over time it also catches up on the more difficult ones.
Thanks.
I have 2 questions. Okay, one, have you already implemented this at DeepMind? Do you already use these algorithms?
So they're not used in general as like a drop-in replacement for matrix multiplication, precisely for the reason I mentioned before, that you need to have a specific use case, that's a specific neural network architecture, and then you can optimize your algorithm for that specific workload. So that is work that is ongoing, but it's a separate research effort to actually have like practical algorithms for the practical use case that we use in production. Like right now, we have from this project algorithms that if you only want to multiply matrices in sequence and do nothing else, then they will be 10 to 20% faster. But usually you also want to do some other computation in between.
And my second question was, can you describe the change of basis in more detail? Because I am having a hard time seeing how you can change basis by keeping everything still as ones and zeros. And
yeah, that's a good point. So when you change the basis, the tensor will no longer just have zeros and ones. Then that's another instance where the tensor will contain potentially other numbers. And then depending on what kind of basis change you choose, you could be getting fractional numbers in the tensor, but we deliberately construct the change of basis or the coordinate system such that it guarantees that the tensor is still integer valued, just for convenience.
Yeah. Do you have any theory of why it's necessary with the Monte Carlo tree search and why the model can't estimate it by itself?
Sorry, can you repeat?
Do you have any theory why the model can't estimate the values and policies without the Monte Carlo tree search?
Yeah, that's a big question. I don't have a theoretical answer, but just like intuitively, is that you actually spend more computation when you get the estimates from the tree search. Because when you just arrive at some state and you query the neural network, you just query the neural network once. So you invest the computational resources required to do one forward pass through the neural network. That gives you some prediction of the value and the policy. But then when you actually do the tree search, you go look deeper into the tree. And when you look deeper into the tree, you know the exact environment, you know the exact rules of the game. So you see what actually happens when you take some number of steps, and so that's one benefit, that you see the true future. And then in the true future, you keep querying the neural network on more children, more descendants of the current node. So you'll actually invest more computation. Like the overall estimate that you will form for which action to take from the current state will be based on many more network evaluations, some of which are done deeper down in the tree, at which point the game is supposed to be simpler because you're already closer to the end of the game. So those predictions might also be more accurate. And so the answer is that you have invested more computation to form a more accurate prediction by querying the neural network many more times, and some of those queries will be done in states that are maybe easier for the neural network to give you a good answer on because they are closer to the end of the game.
Thank you.
So you mentioned that the architecture was very important. I was wondering if there were any other things beside the attention that were very key to the result, and if there were some things that you tried out and didn't really work or didn't improve. So if you can comment a bit on that.
Yes, on the neural network side, we tried a huge number of things, and many of them did not work. Often these were instances where we thought that mathematically this is an idea that makes complete sense and will certainly improve the system, and then it just didn't. The most maybe prominent example is that often people who design neural network architectures, they will try to build in symmetries of the problem into the architecture. So for example, when you know that your problem is symmetric under permuting the axis of a tensor, then you will try to make sure that the architecture is equivariant or invariant under the same symmetry. And we developed multiple architectures that were taking into account the symmetries of the problem. And in most cases, they did not actually perform as good as the one that we ended up using at the end. So I think that's the one example where we spent most of the time and didn't actually translate to better results.
Do you have intuition on why?
Just the general one that maybe mathematically it's true that you have this symmetry and that architecture should be better, but when you change the neural network architecture, it also changes the landscape of the loss when you optimize the neural network. the parameters of the neural network. So it might be that like the best possible neural network would exist in this restricted space of equivariant architectures, but you're just not able to find it because the landscape of the loss is changed. That's the only one I have.
I also have a question. I might be wrong here on how this works, but I understand you kind of give it like a tensor, and then it has to do like a rank decomposition, right?
Yeah.
And what you said as well, if you give it like multiple matrix multiplications as a tensor, right? It gets better on a specific one also. And also in the beginning, right, you train it on synthetic, kind of off-the-shelf decompositions of a lot of configurations. So wouldn't it make sense to just give it also in training a lot of random tensor configurations and then kind of use these to construct like decomposition training on the network? And then it might be also better if you then give it like the matrix multiplication initial state as a decomposition. Did you try that, and did that work or not?
Yeah, so there are two components to that. One is that we actually do keep training on the synthetic demonstrations throughout the procedure. So it's not like we only train on synthetic demonstrations initially and then we only train on matrix multiplication tensors. Initially we thought this separation would make sense, but then we found that by keeping the synthetic demonstrations throughout the training, it actually keeps improving performance also at the end, surprisingly, for reasons we don't fully understand. So one answer is that we do keep training on the synthetic demonstrations throughout. But I think you were also referring to the possibility of having the actors try to decompose the random tensors. So not only have the actors always start with a matrix multiplication tensor, but also start with other tensors. We did try that, but that didn't help us. And one reason might be that because of how we generate the synthetic demonstrations, it might actually be quite likely that the decompositions are already optimal for the tensor. And in that case, it wouldn't provide anything new by having the agent play those games because we already have the optimal trajectory for them. That's our guess.
You mentioned that before what was that? The tensor is inputted to the policy network or the learner. It is down projected into 3 different 2D matrices, if I remember. Could you please elaborate on the intuition behind doing that, and why does it help? Why does it make sense?
Yeah, those are very good questions with no good answers. So I would say the main motivation is maybe computational. So this tensor, here I'm showing just a small case, 4 by 4 by 4, corresponding to 2 by 2 matrix multiplication. But the actual size that we're most interested in was 5 by 5 matrix multiplication, in which case this tensor is of size 25 by 25 by 25. Now, I cannot quickly do this arithmetic in my head, but this tensor roughly has thousands of elements inside it. And if we wanted to do self-attention on all these elements simultaneously, then it would just be a expensive operation. And of course, like nowadays, people do self-attention on thousands of elements at the same time, but we also have the additional requirement that the neural network should be very fast at inference time. Because as I mentioned, most of the compute is spent in acting, and in acting, to decide on every single action that the agent plays, it needs to build this tree search, and whenever you add a new node in the tree search, you have to query the neural network. So you're querying the neural network really a huge number of times, and it's very important for the neural network to be very fast at inference time. So we are looking for architectures that would be not only modeling the problem in the best way, but also be very fast. And having this 3-dimensional cube and doing self-attention on it was just very expensive. So we looked at ways of how to simplify the problem, make it cheaper, and getting like the 3 2D projections was like one natural idea how to reduce the number of elements that represent the tensor, because then you have like 3 n squared entries instead of n cubed. So that's the main motivation.
Right, thanks.
Hi, wonderful and clear talk, thank you. Sorry. Okay, so I was wondering, we talk about architecture, but from my tiny experience about Monte Carlo research, I've noticed significant improvement if we change the algorithm, for instance, to UCT or RAVE or something like that. Have you noticed any significant impact on that? Thanks.
We did play with variants a little bit, like RAVE as well. There were some improvements sometimes, but then in the end, we also tried to take the overall system that we had and try to also simplify it as much as possible, only keep the key ingredients. And in the end, this was not a key ingredient that would make a huge difference. The important ones were the 4 ones I mentioned in the talk.
So, if there are no further questions, let's thank our speaker again.
Thank you.